Section: Introduction. After we deploy a machine learning model, there might come a time when we need to update the model because we can't use some of the data it was originally trained on. This could be due to laws that allow people to ask for their data to be forgotten or because some of the data might not be reliable. Machine unlearning is the process of adjusting a model so it acts as if it was never trained with certain data in the first place. Basically, if we have a piece of data we want to forget and a model trained on a dataset, our goal with machine unlearning is to tweak the model so it's like we never used that piece of data for training. The straightforward way to do this is to train the model again without that piece of data, but we're really interested in finding a way to do this that doesn't take as much time or resources. Previous work has found quicker ways to unlearn for certain types of algorithms, but when it comes to deep neural networks, DNNs, the methods we know about still take a lot of time and might not work as well afterwards. Even though we've figured out efficient unlearning for some methods, finding ways to do this for deep neural networks remains a challenge, especially because training these models on big datasets can be very costly. We've noticed that the way large language models, LLMs, learn gives us new ideas for quickly and accurately unlearning with deep learning. LLMs usually learn in 2 steps. First, they learn in a general way that doesn't focus on a specific task, and then they learn how to do a specific task. We've found that during the second step, when we're teaching the model a specific task using something called in-context learning, it's easier to unlearn data. In-context learning involves giving the model a prompt that shows what we want it to do, using examples. This method has been shown to work as well as, or even better than, other methods for some tasks. With in-context learning, we don't have to change the model itself to unlearn something, which is great. But we do need to be careful about which examples we choose to use in our prompts, especially if we want to forget some of the data. If we had chosen different examples without the data we want to forget, the outcome might be quite different. This can be a bit tricky if the way we choose the best examples depends on looking at all the data we have. In our work, we introduce a new way of doing in-context learning that's just as accurate as other methods but makes it easier and less costly to forget data. Our method involves grouping the examples and then picking the ones that are most representative of each group. However, unlike previous methods, we use a special way of grouping called quantized k-means, which makes it easier to adjust the groups if we need to forget some data. We call our method erase. We've tested erase and found that it works well, offering a good balance between accuracy and the ease of forgetting data. This is a step forward in solving the problem of unlearning for deep learning models. However, we've also noticed a new issue. Changing how we train the model to make unlearning easier can make other parts of using the model more costly. Specifically, using in-context learning can make it more expensive to use the model because of the extra steps involved. To better understand the overall cost of unlearning, we've come up with a new way to measure it, taking into account not just the cost of unlearning but also the cost of using the model. This helps us see the trade-off between making it easier to forget data and the potential increase in costs elsewhere. Our findings suggest that in-context learning can still be a good choice for situations where unlearning is important, even when we consider these additional costs. In summary, our main contributions are exploring how to unlearn with in-context learning methods, proposing a new way to measure the cost of unlearning that considers more factors, and introducing erase, a new unlearning method for in-context learning that's efficient and works well. Our work shows that in-context learning can be a practical option for situations where we need to be able to forget data efficiently. Section Summary. The section discusses the concept of machine unlearning, which involves modifying a machine learning model to behave as if it were trained without including a certain data point. It highlights the challenges and costs associated with unlearning, particularly in the context of deep neural networks, and introduces an in-context learning algorithm called erase that offers efficient exact unlearning operations with performance comparable to other methods. Additionally, it proposes a new holistic metric for evaluating unlearning costs, taking into account both the unlearning operation cost and inference cost, and demonstrates the efficiency of in-context learning for unlearning, making it favorable for domains requiring exact unlearning. Section: Related work. We've looked into the existing research on how to efficiently remove data from deep neural networks, a process often referred to as unlearning. This concept of unlearning is about making a model behave as if it never learned a specific piece of data in the first place. Researchers have tried different ways to measure how well unlearning works, like checking if the model's predictions change significantly or ensuring that the data can't be reconstructed to protect privacy. However, there's no agreement on the best way to measure unlearning, and it's not always clear if these methods meet certain legal or practical requirements. Unlike these previous studies, we focus on completely removing data from machine learning models without any ambiguity. Previous studies have mainly looked at partially removing data from models and concentrated on the initial training data. Our approach is different because we look at completely removing data, especially during a later stage called task adaptation, which is when a model is fine-tuned for a specific task. There's also research on removing unwanted behaviors from models rather than specific data points, but that's a different topic. When it comes to removing data from models during the task adaptation phase, we revisit some existing methods and their associated costs. We talk about a method called SISA, which stands for sharded, isolated, sliced, and aggregated training. This method divides the training data into equal parts and trains separate models on each part, which reduces the cost of training. If you need to forget a piece of data, you only have to retrain the part of the model that learned that data, which is more efficient. However, when using this method, running the model to make predictions can become more expensive, especially as the number of parts increases. We also explain how we measure the cost of unlearning. We imagine a scenario where we receive requests to forget certain pieces of data one by one, and we look at how much effort it takes to comply with these requests on average. It's important to note that if the requests aren't random, the costs could go up, but we don't dive into those scenarios here. For fine-tuning models, the SISA method is a common way to unlearn data. It involves training several smaller models on different parts of the data, which can make unlearning more efficient because you only need to retrain one small model if a piece of data needs to be forgotten. However, making predictions with this setup can be costly, especially as the number of smaller models increases. We use a specific example to illustrate these costs, focusing on how they scale with the size of the input data. Section Summary. The section, Related Work, discusses the existing literature on approximate unlearning for deep neural networks, focusing on metrics like L_2 distance in weights and model distribution divergence. It also highlights the ambiguity in choosing metrics for approximate unlearning and the potential unsuitability for certain applications like legal requirements. The section, Exact Unlearning Methods for the Task Adaptation of LLMs, delves into prior algorithms for the task adaptation phase of LLMs, emphasizing the unlearning costs of SISA and two baseline algorithms for in-context learning, while also considering inference costs for fair comparison. Section, In-Context Learning. In the section on in-context learning, we discuss how algorithms for selecting in-context learning examples work by choosing a set of examples from a dataset, which are then added to the input for a large language model, LLM. These algorithms don't change the model itself but only the examples that are prepended to the input. If we need to forget a specific piece of data, we essentially need to redo the selection process as if that data was never there. A simple way to do this is by randomly choosing examples, which is easy to adjust if we need to forget something, making it a low-cost method for unlearning. However, random selection might not always give us the best results in terms of accuracy. For tasks where accuracy is key, a method called auto chain of thought, ACOT, can be more effective. This method groups the data into clusters and picks the example closest to the center of each cluster. If we need to forget a piece of data using ACOT, we have to redo the clustering, which can be costly depending on the size of the dataset. We then introduce a new method that aims to be as accurate as ACOT but without the high cost of adjusting if data needs to be forgotten. This method, called erase, efficient removal and selection of examples, also groups data into clusters but uses a technique called quantized k-means. This technique makes it easier to remove data from the clusters without needing to redo the entire process, thus keeping the cost of unlearning low. However, there's a trade-off between making unlearning easier and the accuracy of the clustering, which is controlled by a parameter in the quantized k-means method. In summary, we're looking for ways to select in-context examples for LLMs that are both accurate and easy to adjust if we need to forget certain data. Our new method, erase, offers a promising approach by balancing these needs through a specialized clustering technique. Section summary. In-context learning involves selecting a set of in-context examples from a dataset to prepend to the input given to a language model, LLM, with unlearning in-context learning algorithms aiming to reproduce the distribution of in-context examples. Random sampling has a constant unlearning cost with respect to the dataset properties, while the auto chain of thought, ACOT, algorithm, which is more effective for certain tasks, has unlearning operation costs that scale with the dataset size. A new algorithm called erase, efficient removal and selection of examples, is proposed to address the gap for an accurate in-context learning algorithm with an unlearning operation cost that does not scale with the size of the dataset, achieving dataset size independent unlearning of the clusters using quantized k-means. Section on more holistic unlearning costs. We're discussing the costs associated with unlearning operations in large language models, LLMs, specifically focusing on how in-context learning can make these operations more efficient during the task adaptation stage. However, we've noticed that making these unlearning operations more efficient can actually lead to higher costs elsewhere, particularly when it comes to deploying the model. For instance, it's not widely discussed, but using a method called NSISA can increase the costs of making inferences. Similarly, in-context learning methods also bump up these inference costs, even though they make unlearning more efficient. This becomes a significant issue when there are many test queries for each unlearning request, potentially making these methods more expensive than the standard approach of fine-tuning with one SISA. To better understand these costs, we've introduced the concept of holistic unlearning cost. This is a way to measure at what point the cost of using a certain algorithm becomes as expensive as the baseline method, fine-tuning with one SISA. We calculate this by comparing the number of test queries per unlearning request that can be made before the costs match up. This calculation helps us see when methods like NSISA or in-context learning become more expensive than the baseline fine-tuning methods. Our approach is inspired by previous analyses that have looked at the performance of in-context learning compared to fine-tuning, especially in terms of computational resources. In our experiments, we're testing our method, which we've named erase, against other in-context learning methods and the standard fine-tuning with SISA. We're looking at how well each method performs in terms of test accuracy and holistic unlearning costs. Our goal is to see if erase can match or outperform a method called ACOT and whether task adaptation using erase or other in-context learning methods is more cost-effective for unlearning than using SISA. For our experimental setup, we're using large language models with a causal decoder architecture, specifically choosing Llama as our base model because of its popularity and performance across different pre-training procedures. We've selected 15 tasks from the Big Bench project, focusing on those that are particularly challenging for LLMs and lack instructional content. We've made sure each task has enough examples for fine-tuning and evaluation, excluding any that don't meet our criteria or are unsuitable for our evaluation methods. To ensure a broad dataset, we've also included additional tasks from Big Bench that Llama struggles with. When it comes to fine-tuning, we're using a specific pipeline and focusing our updates on the log probabilities of answer tokens, ignoring other parts of the input. We're using a block size of 256 tokens and a batch size of 8, with the Atom optimizer and specific settings for beta values, weight decay, learning rate, and warm-up steps. More details on our prompts and fine-tuning setup can be found in the appendix. Section summary. The section discusses the trade-off between inference cost and cost per unlearning operation in the task adaptation stage of a language model, LLM. It introduces the concept of holistic unlearning cost, which measures the number of inferences per unlearning request upon which a modified learning algorithm becomes as expensive as the baseline. The effectiveness of the proposed method erase is explored in comparison to other in-context learning methods and the unlearning baseline of fine-tuning with SISA, in terms of test accuracy and holistic unlearning costs, using a suite of 15 challenging tasks from the Big Bench dataset. Section: Evaluation Setup. We set up our evaluation based on the guidelines provided by the Big Bench dataset. In our study, we focused on tasks formatted in JSON, which are assessed using two main types of metrics, generative and multiple choice. For generative metrics, our model had to create text based on a given input, and this output was then compared to a correct answer that was either unformatted or minimally formatted. On the other hand, multiple choice metrics involved evaluating our model's choice from a few options, determining the most likely answer or comparing the model's choice distribution to the correct answer distribution. We preferred metrics based on log probability for multiple choice questions because they offer a more gradual and predictable way to track changes in our model's performance. We reported our model's performance on these tasks by using a normalized score, where 0 means the performance is as good as random guessing, and 100 is equivalent to the performance of a human expert. We compared our erase method to other in-context learning algorithms that weren't specifically designed for unlearning. Specifically, we looked at how erase stacks up against ACOT, especially when ACOT performs better than just randomly picking examples, which shows the importance of selecting examples for efficient unlearning. We found that both erase and ACOT generally did better than random selection, indicating that methods that are harder to unlearn actually perform better. In most cases, erase outperformed ACOT. We also explored if reducing the dimension of data, using a technique called UMAP, before clustering would affect the performance comparison between ACOT and erase. It turned out that dimension reduction slightly improved or matched the performance for both methods, but overall, it didn't significantly change the performance comparison between ACOT and erase. Next, we questioned whether our erase method could match the performance of SISA variants, which are a baseline for fine-tuning models with unlearning capabilities. We compared ERASE's performance using different numbers of in-context examples against SISA's performance using different numbers of shards. Increasing the number of in-context examples or shards generally increases performance but also raises the cost of inference. Our findings showed that erase, with just 3 or 4 in-context examples, could achieve accuracy comparable to all SISA variants on several tasks. This suggests that in-context learning, particularly with a few examples, is not only effective but also more efficient in terms of unlearning costs compared to SISA. Finally, we looked at the overall cost of deploying in-context learning versus SISA when it comes to unlearning requests. We measured the cost in terms of flops, floating point operations per second, for both unlearning operations and inference. Our analysis revealed that the unlearning costs for in-context methods are practically zero, making them more appealing for models that need to be frequently updated or corrected. However, when we considered the number of inferences per unlearning request, in-context learning, especially with 4 examples, turned out to be more costly than SISA. But with 2 or 3 examples, in-context learning was more efficient than the most efficient SISA variants for many tasks. This led us to conclude that in-context learning, particularly with a smaller number of examples, offers a more cost-effective solution for tasks that require frequent updates or corrections. Section Summary. The evaluation setup for our performance assessment follows the Big Bench dataset process, using JSON tasks with generative and multiple choice evaluation metrics. We prioritize log probability-based multiple choice metrics and report performance using normalized aggregate scores. Comparing erase to ACOT and random selection, we find that erase outperforms ACOT on 3 out of 4 tasks and has comparable accuracy despite having more efficient unlearning operations. Additionally, we observe that 3 or 4 shot erase can be as accurate as all SISA variants for several tasks, making in-context learning holistically more cost-efficient for unlearning than SISA. Section: Discussion. We're diving into a discussion about the costs associated with completely removing data from machine learning models, a concept we're calling holistic unlearning cost. We're curious if there's a way to determine the minimum amount of resources needed to achieve this efficiently without sacrificing the model's accuracy. Specifically, we're pondering if there's an unavoidable give and take between the resources used for making predictions and those needed for the unlearning process in certain machine learning scenarios. If such a limit exists, it would mean there's a balance between the amount of data a learning algorithm can ignore or unlearn without any action, and how easily this capability can be verified. We think this issue is crucial for the broader machine learning community as it highlights the inherent challenges in completely removing data from models. We also want to clarify the difference between two types of unlearning: exact and approximate. Approximate unlearning tries to mimic exact unlearning closely enough for specific purposes. However, the need to unlearn can arise from various practical reasons, like legal or performance issues, that don't fit neatly into any single measure, making approximate unlearning tricky. On the other hand, exact unlearning isn't perfect either. It can be hard to verify or audit, and might still risk exposing private information if, for example, someone can compare the model before and after unlearning a particular piece of data. Meeting additional privacy or legal requirements could alter the balance between prediction and unlearning efforts we've noticed, as well as the preference for learning methods that adjust based on the context. Moreover, we've assumed that unlearning requests come one by one, but grouping them into batches could make the process more efficient, as the cost wouldn't increase with more requests. When it comes to learning within a specific context, our observations showed that one method, erase, often matched another, SISA, in accuracy. But this wasn't always the case, and the effectiveness varied significantly depending on the task. We haven't found any research that predicts when learning within a context will work well compared to more traditional methods like fine-tuning, nor can we fully explain why some tasks work better with this approach than others. Identifying when and why in context learning is effective without having to resort to comparisons remains an important question for future exploration.